So welcome to Math 140. This is lecture 21. And what we're going to be doing today is we're going to be continuing our discussion on sequences and series, hopefully finishing that up, and then moving to some applications of calculus for Monday's lecture when we will potentially have some other perspectives. So I want to continue talking about different tests of convergence. I want to give a proof of the ratio test. I'm going to state the root test and not give the proof. The proof is very similar to the proof of the ratio test. You can have large discussions as to which is the better test, ratio or root. And then the question is, what do you mean by better? Better could be easier to implement. Better could also be works for a larger class of sequences and series. So the comparison test is wonderful if you know what to compare it to. If you don't know what to compare it to, it's very hard. Comparison test requires art. Ratio, root test, integral test, for the most part, these are pretty straightforward if you can do algebra. The integral test, you have a little bit of work that you have to do. You have to figure out what function should I use. We'll almost always just do a search and replace. If the index is n, just wherever you see an n, put an x. And that will almost always work. Okay, so our go-to sequence is always the geometric. And if we have, 1 plus r squared plus ... that equals 1 over 1 minus r if the absolute value of r is less than 1. And so we're going to use the geometric series test to prove convergence in many other situations. And so the first was the ratio test. And here we're going to let rho be the limit, if it exists, as n goes to infinity, of an plus 1 over an. And then if rho is less than 1, it converges, greater than 1, it diverges, equals 1, no information. And we saw last time examples where it equaled 1, where unfortunately it could diverge for one of the examples and converge for the other. So there really is no information when it equals 1. So the proof is as follows. Let's assume rho is less than 1. So there is an epsilon greater than 0 such that 0 is less than rho is less than 1 minus epsilon is less than 1. So what I'm doing is, if it's less than 1, it has to be less than 1 by a certain amount. If it's converging, let's say it's converging to 0.99, then at some point it's got to be less than 0.999. So all I'm saying is, oh good, we do have a Java update today. I was so worried. So all we're saying is that since it converges to 1, eventually it's got to be close to some number less than 1. So let's just call that, we know that number is rho, but I'm going to write explicitly it's at least some distance from 1. So now this means there is a big N such that for all little n bigger than or equal to big N, we have an plus 1 over an is less than or equal to 1 minus epsilon. Because the limit goes to 1, goes to rho, which is less than 1, eventually each of these fractions is going to be at most 1 minus epsilon. So this means an plus 1 is going to be less than or equal to an times 1 minus epsilon. Everybody comfortable with that? I'm just taking little n to be big N, the first term in the sequence. And then we would know that an plus 2 would be less than or equal to an plus 1 times 1 minus epsilon. But what do I know about an plus 1? What's true about an plus 1? Right, so this is going to be less than or equal to an times 1 minus epsilon squared. What do I know about an plus 3? That's less than or equal to an plus 2 times 1 minus epsilon. So what is that going to be less than or equal to? So what is an plus 3 in absolute value going to be less than or equal to? So an plus 2 was less than or equal to an plus 1 in absolute value times 1 minus epsilon. We substituted for an plus 1, which was at most an times 1 minus epsilon, and we got an plus 2 was at most absolute value of an times 1 minus epsilon squared. Now we have an plus 3 absolute value is less than or equal to an plus 2 absolute value times 1 minus epsilon. What should we substitute? Here, an 1 minus epsilon cubed. We just substituted for an plus 2 in absolute value from the previous line. And so we would then have a 1 minus epsilon cubed. What would the next term be? It would be at most an times 1 minus epsilon fourth, then 1 minus epsilon fifth. And so the tail sum, if we looked at an plus 1 plus dot dot dot, that's going to be less than or equal to an times 1 plus 1 minus epsilon plus 1 minus epsilon squared plus 1 minus epsilon cubed plus dot dot dot. What kind of series is that? Geometric series. And the ratio is less than 1, so this is equal to the absolute value of an 1 over 1 minus 1 minus epsilon, which is just going to be an times epsilon, times 1 over epsilon. And that proves that the sum converges. So the ratio test is really just doing a comparison test. What's the hardest part about doing the comparison test? When you have to do the comparison test, what's the most difficult, challenging part of it? Figuring out what to do. I feel like I'm selling Gitsu knives. But look, this will give you for free what to compare it to. It's going to compare your sequence to a geometric series. If rho is less than 1, so what this says is ratio is a comparison test, but you do not need to find the sequence. You don't need to find the sequence to compare. That's the worst part of the comparison test. So rather than finding the sequence to compare, it is going to compare it to a geometric series that converges. All we have to do now is do the algebra. So for example, let's do one of the most important examples of all. E to the x is the sum and goes from 0 to infinity of x to the n over n factorial. So if I were to write that as, an, or really an of x, what would an be? X to the n over n factorial. Let's see if this converges. And if so, for what values of x does it converge for? What values of x do you hope it converges for? Oh, right, this is the exponential function. We've never told you the exponential function only works if x is at most 1 or at most 5 or at most 1,000. So we hopefully will see something that converges for all values of x. So let's calculate. So rho, and I'll call it maybe rho sub x to remind ourselves that this calculation is depending on x. So let's look at rho sub x. It's going to be the limit as n goes to infinity of an plus 1 of x over an of x. So this is the limit as n goes to infinity, x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. Okay, so how do you divide two fractions? You multiply by the reciprocal of the denominator. So this is the same. If I have a over b over c over d, this is just a over b times c over d. Because if I multiply by c over d over c over d, it cancels the denominator. Oh, sorry, d over c, d over c. Sorry, d over c. D over c. Because if I multiply by d over c over d over c, it cancels the denominator and makes the denominator 1. So this is just going to be the limit as n tends to infinity of x to the n plus 1 times n factorial over x to the n plus 1 factorial. And now we have massive algebraic depth. What's x to the n plus 1 divided by x to the n? X. Now, what about n factorial divided by n plus 1 factorial? What does that equal to? So remember, n factorial is n times n minus 1, 3 times 2 times 1. N plus 1 factorial is n plus 1 times n minus 1, 3 times 2 times 1.
1 over.
Yeah, it's just 1 over n plus 1. This is just going to be n plus 1 times n factorial. So we just get x over n plus 1. X is fixed. So for fixed x, as n goes to infinity, what does this go to? It goes to 0. Equals 0. So converges for all x. Yes.
It's going to be like a dumb question, but is there like a certain turning point for all functions where they go from like diverging to converging?
Depends on the function. So there's a beautiful passage in a phenomenal book. If you talk to any PhD mathematician who has earned their chops, if you say Baby Rudin or the Little Blue Book, they will know immediately what you're referring to. It's called Principles of Mathematical Analysis. And they try to talk about, can it be a boundary between whether or not you have convergence or divergence? So the example I'm going to do is from that wonderful, wonderful book. So let's consider the sum n goes from 1 to infinity of 1 over n. Converges or diverges? Diverges. This is the harmonic series. Diverges. We could do the integral test. We could do grouping. We know that this diverges. So if we want to make it converge, what do we have to do to the denominator? Make it larger. So let's make it a little bit larger. Let's look at the sum n goes from 3 to infinity of 1 over n natural log of n. And you know what? At this point, I'm playing the professor card. We're going to write LOG for the natural log of n. Because I don't like n, ln, n. This is just a nightmare with my horrible handwriting. So LOG is natural log. Welcome to college. Okay, we're going to use the notation LOG. So I've made the denominator a little bit larger. Why am I not starting the sum at 1? Good, so convergence average, but yeah, log of 1 is 0. And so if I started the sum at 1, I would actually have it's 1 over 0. Okay, it's really not going to be that much of a challenge to determine if it's going to converge or diverge. I'm starting off with plus infinity. So let's start off with I could have started off at 2. So let's start off with So we could try to do this with what test? Ratio test will not work. 1 over n, when we did the ratio test, gave us just 1 for the limit. You'll still get 1 if you have 1 over n log n. So let's do the integral test. So what would f of x be? Yeah, basically search and replace, try 1 over x log x, and use the integral test. So we'd have the integral from 3 to infinity of 1 over x log x dx. This looks like a challenging integral, but it's actually not so bad if you use the right integration technique. And by right integration technique, I don't mean go to Wolfram Alpha or Mathematica or something like that. This is something you can do with pen and paper. What methods would you try to do for this? What integration technique can we try?
We separate it to 1 over x minus 1 over log x.
We could do that. And then what would you do once you have that?
See where we are from there.
I mean, it's basically the same as what we have here. We need an integration technique. Remember, baby is crying. You got to do something. What do? Give me some possibilities. I'm sorry. So we could do integration by parts. So if we want to do integration by parts, we would have to choose a u, we would have to choose a dv. So for one of them, I would have, okay. We could try to do this. Does anybody have a choice of what they want for u or dv? Okay, remember it's in the denominator, so it would have to be 1 over log x. And so if we take u to be 1 over log x, if we then try to take the derivative, we start off with log of x to the -1, you would get negative 1 over log squared of x times 1 over x. It's getting worse. We could try it. We could see what happens. So we would get u is equal to 1 over log x. Du would be negative 1 over log of x squared. And then the derivative of log x is 1 over x dx. dv would be 1 over x dx. What would v be?
Log x.
Log x. And so we would get that the integral from 3 to infinity of 1 over x log x dx would be uv. Oh dear. Right, what's uv? 1. So we would get 1 evaluated at 3 and infinity. And then we would have a minus v du, which just becomes a plus integral from 3 to infinity. Now, v du becomes really interesting. Right? What do you get? You get 1 over x log x dx. So we return to where we start. So this just as bad. But this is actually a little strange. So, I mean, we could, instead of integrating all the way to infinity, we could integrate to just some finite number, and then we would no longer have infinity, but we have exactly the same expression on both sides, not with a minus sign. And so I'm just quickly checking to see if we've made an algebra mistake somewhere. We have 1 over 1, so we have log x to the -1, so we have negative. Yeah. So this is no information, this doesn't help, right? So you could, of course, then try the other way. You could try maybe u equals log of x, and then you would need the antiderivative of, I'm sorry, then you would need the derivative of that, which is 1 over x. No, I'm sorry. We could try u equals 1 over x. So its derivative would be basically like a 1 over x squared. dv would be a 1 over log x. And then we would need to find what function has derivative 1 over log x. So it seems like integration by parts is not a good approach. Okay, that's fine. Let's try something else. So integration by parts failed. What else can we try? Use substitution. So what should we try for u? There is a good choice of u here. So I would try just log x over x log x. X log x is very complicated. If you choose x log x, and then you start to do the calculation, your du is going to involve the product. Let's take u to be log x. It's been a while since we've done a calculation of this. So du dx is just 1 over x. So du is 1 over x dx, right? Well, there was a comment about maybe splitting this up and writing it as maybe like 1 over log x, 1 over x dx. Gee, if I write it like this, it almost looks like we're living life well, right? We've got a 1 over x dx. That's exactly our du. 1 over log x becomes just u, okay. As x goes from 3 to infinity, what does u go from? Yeah, and what's the log of infinity? Infinity. So this would just be the integral. U goes from the log of 3 to infinity, 1 over u du. Oh, okay, well, what function has derivative 1 over u? Log u. Evaluated at the log of 3 and infinity, so it diverges. Okay. Now, I'm going to press a card. So I'm going to take this, I'm going to copy the slide, and I'm going to essentially do a search and replace. Let's look at x log x squared. Let's just put a square there. Okay. If I put a square there, u is still, we take to be log x. Du dx, we still get 1 over x dx over du. The range of u is the same. The only difference now is I have a log squared, so this becomes a 1 over u squared, right? And so now, what do I get? So I get negative u to the negative 1. I was using the wrong sheet. It's cheating, I know, but it's faster than using the eraser. Okay. So we get, this is negative u. Oh, so this is a u. Wait a minute. Oh, I must have erased too many things. Okay, that was a squared. That was a squared. So that's a squared. So negative u to the negative 1 at the log of 3 and infinity, right? Trying to make sure I didn't erase anything from the previous page. No. Well, because I have a negative sign out front, I can flip the order of my bounds, right? So this is going to just be 1 over u at the log of 3 and infinity. And that's just equal to 1 over the log of 3, which converges. So the sum of 1 over n log n diverges. The sum of 1 over n log n squared converges. So we're trying to talk about, is there a boundary between? And then you can play even more games. You could look at the sum of 1 over n log log n versus the sum of 1 over n log n squared. Okay. Which do you want to do? The one on the left or the one on the right? Left. Do you think that's going to converge or diverge? I am a naive person. If I'm talking about a line between convergence and divergence, I should probably be giving you one example that converges and one example that diverges. Do you think the one on the left will be the converging or the diverging? Diverging. Its denominator is a little bit smaller, not by much. If n is huge, let's say n is e to the 1,000. You take a log, you get e to the 1,000. You take a log of that, you get 1,000. That's a very small difference. So what we could do is we could do the integral test. Let's say now I'm going to go from n goes from 9 to infinity. Why do you think I'm starting at 9? Why am I not starting at 3 as I was before? Yeah. Can you take the log of a negative number? No, I have to make sure that I start deep enough so that I don't have a negative number. I have a log. Okay. So I want to write this as an integral. So I'm going to write it as an integral of 1 over log n, 1 over log n, 1 over n. I'm sorry. And I'm going to make all these x's. Dx. So I'm trying, f of x equals 1 over x log x log x. How do you think we should handle this integration? So try your substitution. What should we try for u? So we could try log x. Does anybody have any other candidates? Let's survey the field, and then we might decide to do log x. It worked before, but maybe we want something different for this problem. Any other candidates to try? I'm sorry? We could try 1 over log. But again, when you differentiate that, it's then going to be bad. As we've got log x, we've got 1 over log x, and think of at least one other good candidate to try. Well, if we try u equals x, there's no change. So we need another candidate. We could try log of x. Any other thoughts? All right, somebody buzzed in, but they did not answer. So or maybe that buzzer meant the log x was the right thing to try. I'll view it that way. So if we try u equals log x, what's du dx going to be? So it's the chain rule, right? We'll take the derivative of log x and then multiply that by the derivative of the inside, the log x. So what's the derivative of the log function? The 1 over function. So this becomes 1 over log x, and then the derivative of log x is 1 over x. So du is 1 over log x, 1 over x dx. Oh, come on, this is nice. Right? So if we choose u to be log x, then we are getting the integral u goes from log of 9 to infinity of 1 over u du. And what does that equal? It equals log u and so this is infinity, so it diverges. So you really can get two sequences that for a long period of time don't differ by that much. I did n log n. What would be the next one? I could do n log n log n. I'm sorry? Well, squared, and the squared one will converge. So if I wanted to get something that's a little bit smaller that still diverges, after this I could go n, in my denominator, I could go n log n log n log n. And if the other one had log n cubed, it would converge. And I could go n log n log n, that would diverge. And so you can have these series that are really close and are different by very small amounts. So you can have a real fine line between them. So this is a really good problem in terms of just trying to understand how to use all the results. It is a great example of the integral test. The hardest part of the integral test is figuring out either what function to use, which most of the time actually isn't that bad. Just replace the index with x, and then doing the resulting integral. So the more choices you have in doing the integration, the harder it is. And so what you want to do is you want to just have a list of techniques and just go through them like crying baby and eventually hope that one of them works. Integration by parts is not a bad thing to try. But unfortunately, when we start looking at the derivatives, oh, I think it copied. So when we tried integration by parts here, it caused some trouble. And then we showed over here that it diverged by doing a u substitution. When we put in squares, it was fine. So The slide seems like it was repeated. Okay. So now the sides have been fixed. Okay. So now the next one is the root test. So let's let rho equal the limit as n goes to infinity of the absolute value of an to the 1 over n. If it is less than 1, greater than 1, equal. What do you think is going to be true if it's less than 1? Do you think it diverges if it's less than 1? What should we have for the ratio test? So it converges if rho is less than 1. What would you guess over here? Okay, I've got 3 conditions just like the ratio test. Probably the same. So if it's less than 1, it's going to converge. If it's greater than 1, it's going to diverge. And if it equals 1, we have no information. So I'm not going to go through the proof. The proof is similar and it involves looking at, comparing it to a geometric series. Proof is similar to ratio compares to a geometric series. All right. So let's try to do an example. Give me an example of a situation where the ratio test failed. 1 over n. Let's see if the root test can win. So let's consider the sum. N goes from 1 to infinity of 1 over n. So an is just 1 over n. So rho is the limit as n goes to infinity of 1 over n to the 1 over nth power. So we're basically getting in the limit 0 to the 0. So what happens? What do you think this goes to? This is the same as the limit as n goes to infinity of 1 over n to the 1 over n. Right? If I have the whole thing to the 1 over nth power, it's the numerator to the 1 over n and the denominator to the 1 over n. So I just need to figure out what is the limit as n goes to infinity of n to the 1 over n. Well, as n gets very large, what does n go to? Nope. As n gets large, what does n go to? N goes to infinity. What does 1 over n go to? So this is looking like infinity to the 0. Irresistible force of movable objects, they meet. Okay, so we have competing influences. This is a hard limit to evaluate. The best way to evaluate is to do a trick. So we want the limit as n goes to infinity of n to the 1 over n. Consider the log of n to the 1 over n. What is the log of n to the 1 over n? Yes. 1 over n times what? Not n, you're close. We have the log of n raised to the 1 over n. So we're using the power rule. The log of, say, x to the r is r log x. So if we have the log of n to the 1 over n, it's just going to be 1 over n times what? I'm sorry? Nope. We're using the power rule. Just log n. So the log of x to the r is r log x. So this would just be 1 over n log n, or just the log of n over n. So if we want to consider the limit as n goes to infinity of n to the 1 over n, that should just be the exponential of the limit as n goes to infinity of the log of n to the 1 over n. If I figure out what n to the 1 over n goes to and I exponentiate that, that should just be n to the 1 over n. Now, if my logarithm is converging to 8, then my original quantity is converging to e to the 8. If my logarithm is converging to 0, my original quantity is converging to e to the 0. All right, so this would just be the exponential of the limit as n goes to infinity of the log of n over n. Well, what's the log of n over n? As n gets really, really large, what does that fraction look like?
0.
Why does it look like a 0? Okay, but how do we know that? So what does the numerator look like? As n gets large, what does the numerator look like? The numerator looks like infinity, the denominator looks like infinity. Do we know any rules to deal with the ratio of infinity over infinity? L'Hopital. Remember, you've made it when your name is a verb, right? L'Hopital it. So so we L'Hopital it. This would be the exponential of the limit as n goes to infinity. What's the derivative of log of n? With respect to, it would just be 1 over n. And the derivative of n is just 1. Ah, okay, well, what is, as n goes to infinity, what does 1 over n over 1 go to? It goes to 0. We exponentiate 0, what do we get? What's e to the 0? 1. So this is just exponential of 0, which is 1. So no information. So unfortunately, the root test gave us no additional information. We did all this great work, but we got no additional information. We at least, though, got an interesting result that we might not have thought of otherwise, that n to the 1 over n is converging to 1. If you think about it, if you take the square root or the 4th root or the 8th root or the 16th root of a large number, what happens to that number? So you take a really big number and you keep taking repeated square roots, what does the number converge to? Have you ever played this game on a calculator where you just keep hitting the square root? If you start off with a big number, and you think, or someone's doing it, you start off with a big number, if you keep taking square roots, what's the saying it's going to converge to? It's going to converge to 1. You know, when you take a square root, you're making the number significantly smaller. If I double n, that's an additional square root, but my number is only increased by a factor of 2. So as n gets really, really large, it's not surprising that a large number is going to be converging down.
You can't go below 1, right?
You can't go below 1 because you start off greater than 1. So at every moment in time, you're greater than 1. In the limit, you could actually equal 1, but you'll never get below 1. Okay, so this is the ratio test. And then again, you could try to, oh, so this is the root test. You could try to do this for other settings. You know, we could try to do the root test for, say, the sum of x to the n over n factorial. So what would be the limit as n goes to infinity of the absolute value of x to the n over n factorial to the 1 over n? Limit as n goes to infinity. We would have the absolute value of x to the n to the 1 over n times 1 over n factorial to the 1 over n. Well, what's the absolute value of x to the n to the 1 over n? What does that equal? So I take x, I raise it to the nth power, and I take the nth root. What do I get? Yeah, I just get back to x, or the absolute value of x here. It's the limit as n goes to infinity of the absolute value of x. Now I need to just calculate what is n factorial to the 1 over n. Yeah, so what could you do? So now we have this 1 over n factorial to the 1 over n. How do we handle that? We could try the log game again. And if you do the log game in L'Hopital's rule, it's going to work out very easily. So you could play logs and L'Hopital. I want to show you another way to handle this. So you want to study the limit as n goes to infinity of the absolute value of x times 1 over n factorial to the 1 over n. Do you agree that n factorial is greater than or equal to n halves to the n halves? No. N factorial is 1 times 2 times n halves plus 1 dot 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 n. And for each of these, you place with n over 2. So I'm making n factorial much smaller by just taking the second half of the terms and just replacing with n over 2. Does everyone agree that this is making my quantity n factorial? This is a really, really small quantity. So n factorial to the 1 over n would be greater than or equal to n halves to the n halves to the 1 over n. What's n halves to the n halves to the 1 over n? What does that equal? So it's going to be n halves to the n over 2n. But what's n over 2n? 1/2. So this is just so it's just going to be the square root of n over 2. So the limit as n goes to infinity of x times 1 over n factorial 1 over n is going to be less than or equal to the limit as n goes to infinity of the absolute value of x 1 over square root of n halves. And what does that limit equal? So as n goes to infinity for fixed x, what is the absolute value of x over square root of x? I'm sorry, square root of n half is going to go to. X is fixed, n is going to infinity. What will this go to? Here. This will go to 0. And so it converges. So this is another way to show convergence. You can show it with the root test. The root test is actually a little bit more powerful than the ratio test. I believe every time the ratio test works, the root test works. I think there are some really obscure situations where the ratio test fails, but the root test works. Which do you think is easier to use in practice? There's a reason I was doing some of these painful calculations today. Yeah, the ratio test is easier to use. Compare what we did for the ratio test to what we did here. We had to be clever. We said, well, we could either do a logarithm and then use L'Hopital, or I could notice that n factorial is at least n halves to the n halves. This is a lot more work. The ratio test, I think, is far more straightforward algebra. So when you are trying to figure out what to do, the more experience you have, the better. What is the easiest test to use if you can use it? Nope. Comparison. Right? If you can directly show I've got a non-negative sequence, which is less equal to something that converges or greater than equal to something that diverges, done. The problem is you have to recognize what to compare it to. So then after that, which tests do you think are the next easiest? Integral or what? Ratio. So which do you think would be easier, ratio or integral? I think ratio is a little bit easier because
some like really hard integrals.
Well, the problem is, can you do the resulting integral? But then on the ratios, it's can you do the resulting algebra? So at some point you have to do something. And the whole purpose of all of this is to get us to the point where we can tell whether or not a sum converges or diverges. So we're going to say a little bit at some point in the semester on Taylor series on trying to replace complicated functions with simple functions. Other things in the queue is we will be talking about applications. So we'll be talking about differential equations. We will do a little bit of physics in this class. We'll talk about motions of planets. I bought a really nice Lego clone set to actually illustrate this, which I'm looking forward to bringing to class. And we'll start doing some applications. I believe we have not yet done the method of least squares and linear regression. Is that correct? Right. So we're going to be doing that as an application lecture. We're going to do, probably on Monday, we're going to do the baseball lecture, applications of calculus to Major League Baseball. We will do a lecture on Monte Carlo integration. So what actually happens when you reach the point where you can't do the integration that you need to do? And it's just too hard to numerically approximate. So it turns out that one of the best ways to integrate is equivalent to just throwing dots on the wall. And in the old buildings, I actually had no problem bringing the dartboard and actually throwing things, because they're going to tear it down. This is, the first year of this new building being really open for everybody, so it's a little bit harder to do something like that. All right, so this is a good place to stop. Have a good weekend.